Welcome to the Deep Dive. We dig into research to pull out the key insights for you. Today, we're looking at something called PHYBench.
That's right. It's a new benchmark, and its whole purpose is to figure out how well large language models, LLMs, can actually understand and reason about the physical world.
So our main source is the research paper introducing it, PHYBench, Holistic Evaluation of Physical Perception and Reasoning in Large Language Models.
Exactly. And it's timely because, LLMs have been showing some really impressive capabilities lately, especially in complex reasoning. Think about things like Math Arena.
Right, tackling those really hard Olympiad-level math problems. So if they're getting so good at that kind of abstract reasoning, what's the missing piece here? What's the gap PHYBench is looking at?
Well, the core idea is that excelling at abstract math or logic problems doesn't necessarily mean an LLM truly gets physics. How things actually work in the real world.
Ah, okay, so current benchmarks might be falling short.
That's the argument. They might be a bit too simple now for the latest models, or maybe too abstract, disconnected from tangible physical scenarios.
And maybe the way we score them is too basic.
That too. Often it's just correct or incorrect. That doesn't tell you much about how the model arrived at the answer, or if it was close, or if its reasoning was sound, but it made a calculation error.
So PHYBench is designed to address these issues. How does it do that?
Well, first off, it's a pretty substantial set of problems, 500 of them. And crucially, they're curated physics problems based on, actual physical situations.
500 is a lot. What kind of physics are we talking about? Does it cover the basics or?
It's quite comprehensive. Covers mechanics, electromagnetism, thermodynamics, optics, modern physics, even some more advanced topics.
And the difficulty? Is it all super advanced university level?
No, it actually spans a range. You've got problems typical of high school physics, then undergraduate level, and even some really tough ones from Physics Olympiads.
Okay, so a broad range of topics and difficulty. What's the really unique feature then?
I'd say a key thing is the type of answer it demands. Models don't just give a number. They have to derive symbolic expressions.
Symbolic expressions,
Yeah,
like equations.
exactly. It forces the model to show its reasoning process using the language of physics, focusing on understanding the underlying principles, not just crunching numbers for a final value.
That does sound different. Can you walk us through an example problem?
Sure. Picture this. You have three small balls hanging one below the other connected by light strings. Then someone strikes the bottom ball horizontally with a hammer, giving it an instant velocity.
Okay.
The question is, what's the instantaneous tension in the middle string right at that moment the bottom ball is struck? And importantly, the models don't get to see a diagram, just the text description.
Right. That definitely requires thinking about forces and how they transmit almost instantly, not just a formula plug-in.
Precisely. It tests that physical intuition and perception.
Yeah.
And to evaluate these symbolic answers, they developed a new metric.
Let me guess. Not just right or wrong.
No. It's called the expression edit distance score, or EAD score.
EAD score. How does that work? What does it measure?
It's based on the concept of edit distance, but applied to mathematical expressions. Essentially, it measures how many changes you'd need to make to the model's symbolic answer to turn it into the correct symbolic answer.
Ah, so it can tell if the model was close in its reasoning, even if the final expression wasn't identical.
That's the core idea. It captures nuances beyond just a binary right-wrong. It reflects the differences in the reasoning process itself.
Did they compare the LLMs to humans on this?
They did. They used undergraduate physics students from Peking University as a human baseline.
And the results? How did the AI stack up?
Well, the headline finding is there's a significant gap. Even the best state-of-the-art LLMs lagged quite a bit behind the human experts in performance on PHYBench.
So that really underlines the limitations PHYBench is trying to expose. Let's recap those limitations of older benchmarks again.
Sure. 1, tasks becoming too easy for modern LLMs. 2, problems being overly abstract, lacking that grounding in physical reality that PHYBench focuses on.
And third, the evaluation methods just weren't cutting it.
Right. Multiple choice or binary scoring, they just don't capture the complex reasoning involved in physics problem solving. PHYBench needed something more nuanced, hence the EED score.
Okay, let's talk about how they actually built this PHYBench dataset. 500 problems is a lot of careful work.
It definitely was. They adapted exercises typically used for humans, high school physics, college courses, physics competitions.
Did they get help?
Yes, they involved quite a few physics students, 178 from Peking University School of Physics, to help contribute problems and refine them.
And the sources for these problems, were they just scraped from the web?
They used a mix, some non-public sources and some public ones, but specifically chosen so they wouldn't be easily found just by searching online to avoid models having simply memorized the
Makes
answers.
sense, and for each problem.
The goal was always to identify a core physical quantity the model needed to solve for, expressed symbolically.
Were there strict rules for inclusion?
Yes, three main ones. First, solvable from the text alone, no diagrams needed. Second, the answer must be a strict symbolic expression, though equivalent forms are okay. Third, the wording had to be completely unambiguous.
Sounds rigorous. What about checking and refining?
Multiple rounds. Problems were reviewed, filtered, human reviewers checked them. They even tested them with LLMs to iron out any clarity issues or formatting problems. And then a final evaluation by 109 human experts.
Okay, let's dive a bit deeper into that ED score.
Yeah.
You said it's based on edit distance between expressions.
That's right. Technically, it's based on the expression tree edit distance.
Expression tree.
Yeah, so first you take the model's answer, usually in LaTeX, and the ground truth answer. Convert both into a format that a symbolic math library, like SymPy, can handle. Then you simplify both expressions as much as possible.
Okay, simplify them first, then what?
Then you can do a basic binary check. Are the simplified expressions mathematically identical? If yes, that's 100% accuracy. But the ED goes further.
Right, the tree part.
The simplified expressions are converted into tree structures. Think of it like breaking down AB plus C into a tree with at the top, A on one branch and a plus node on the other, which then has B and C below it.
I see, like a syntax tree.
Sort of, yeah. Then the algorithm calculates the minimum number of edits, like changing a node, deleting one, inserting one to transform the model's answer tree into the ground truth tree.
And the ED score comes from that number of edits.
It comes from the relative edit distance. That's the number of edits divided by the size of the correct answers tree. This relative distance is then plugged into a function. It's a piecewise linear function, actually.
How does that function work?
If the relative distance is 0, an exact match, the score is 100. If it's very large, meaning the answers are very different, the score is 0. In between, the score decreases from 60 down to 0 as the relative distance increases. So partially correct answers get partial credit.
Interesting. And you mentioned an extension to this, something about subtrees.
Yes, they refined the tree editing algorithm. The idea is that sometimes a model might get a whole chunk of the physics right, represented by a significant subtree in the expression, but maybe connect it wrong or miss another part.
So should we penalize this harshly for that?
Right. The modified algorithm assigns a lower cost for inserting or deleting larger subtrees compared to making lots of small individual node changes. It better reflects capturing a correct physical component, even if the overall solution isn't perfect.
Okay, that makes a lot of sense. So armed with PHYBench and the ED score, what were the main experimental findings when they tested the LLMs?
They tested a diverse bunch of models, including heavy hitters like Gemini 2.5 Pro, Anthropic's O1 model, GPT-4o, and others. The standout result, as I mentioned, was the performance gap.
The gap with humans. Remind us of the numbers.
The human experts averaged about 61.9% accuracy and an ED score of 70.4. The top LLM, Gemini 2.5 Pro, managed 36.9% accuracy and an ED score of 49.5. So yeah, quite a difference.
A big gap indeed. Any other patterns emerge from comparing the different LLMs?
Well, models specifically trained or fine-tuned for reasoning tasks generally did better than the more general-purpose language models, though some recent general models were surprisingly competitive.
What about model size? Did that matter?
It seemed to. The smaller, like 32 billion parameter models performed substantially worse. This might suggest that these really complex, long-horizon physical reasoning tasks are particularly challenging for models below a certain scale or capability level.
And comparing the two metrics, simple accuracy versus the ED score.
They generally ranked the models similarly, but the ED score provided a much wider spread of scores, a broader numerical distribution. This actually makes it easier to statistically distinguish between models.
Easier how?
The ED score turned out to be much more sample efficient. They calculated an average enhancement of 304%.
Whoa, 304%. What does that mean practically?
It means you can get a reliable comparison between models using significantly fewer test problems if you use the ED score, compared to just relying on basic accuracy. That's a big deal for efficient benchmarking.
Definitely. Did they break down performance by physics topic? Like, are models better at mechanics than optics?
Yes, they look into that. They used metrics called absolute and relative advantage to see where different models shone or struggled across domains like mechanics, EM, thermo, optics, etc.
Any interesting takeaways there? Looking at, say, mechanics versus thermodynamics.
There were a few. For instance, some models seemed to find mechanics relatively harder, maybe struggling with 3D concepts or dynamics. Reasoning-focused models tended to have an edge there.
And thermodynamics.
That often requires, multi-step reasoning. And there, the gap between the specialized reasoning models and the general ones was quite pronounced. GPT 4.1 also showed a particular strength in scientific problem-solving across the board.
Did difficulty level within PHYBench make a difference?
Yes, they analyzed that too. Interestingly, Gemini showed a noticeable advantage, relatively speaking, on the harder problems compared to some other models.
Okay, perhaps the most interesting part, did they analyze the types of errors the models were making? What goes wrong in the reasoning?
They did. They broke down the capabilities needed into two broad phases: physical perception, or PP, and robust reasoning, or RR.
Physical perception and robust reasoning. What's the difference?
Think of PP as the initial understanding, reading the problem, identifying the relevant physical objects and principles, making qualitative judgments about the setup. Errors here are fundamental misunderstandings of the scenario.
Okay, like misinterpreting the physical situation described.
Exactly. And RR is more about the subsequent steps: generating the correct equations based on that understanding, and then manipulating those equations, doing the symbolic math correctly. Errors here are more like inconsistencies in the derivation or calculation mistakes.
Can you give an example of a PP error?
In that three-ball problem we discussed earlier, one LLM made a kinematic perception error. It fundamentally misunderstood how the angular velocity would behave in that specific impact scenario. That's a PP failure.
An RR error example.
There was another problem involving a relativistic mirror reflecting a photon. An LLM actually set up the initial physics equations correctly, good PP, but then it messed up solving those equations. That's an RR, equation-solving miscalculation.
So the model understood the physics concept but failed in the mathematical execution.
Precisely. And the researchers point out that the ED score is actually pretty good at capturing both kinds of errors, because both PP and RR failures ultimately lead to incorrect or significantly different symbolic expressions.
It really sounds like PHYBench gets at a deeper level of evaluation then.
That seems to be the conclusion. It effectively tests both that initial physical understanding and the logical mathematical reasoning that follows. It's a benchmark for AI's ability to handle the kind of rule-based symbolic reasoning that's just fundamental to science and engineering.
So the big takeaway here is, despite all the progress LLMs have made, especially in things like math, there's still a pretty clear gap when it comes to understanding and reasoning about the physical world like humans do.
Yes, PHYBench really highlights that gap. It shows that grasping physical principles and applying them correctly in complex scenarios is still a major challenge for current AI.
And PHYBench itself, along with the ED score, offers a much more insightful way to measure progress on that front.
Definitely. It provides a more nuanced, comprehensive picture than we had before.
Okay, leaves us with something to think about. Given these demonstrated limitations, especially in physical perception, what kind of fundamental breakthroughs might AI need to truly grasp the complexities of the physical universe? Something to ponder. Thanks for exploring PHYBench with us.